40 light-years from where you are sitting, right now, a star is burning, not the way our sun burns, not with the confident, steady hydrogen brilliance that has warmed this planet for 4.5 billion years. This star is smaller, redder, older than the solar system by 3 billion years. It burns dimly like a coal left at the edge of a fire, and it has been burning that way since before the Earth had continents. Around it, locked in a gravitational clockwork so precise it borders on the musical, orbit 7 worlds, 7 Earth-sized planets, 3 of them sitting exactly where liquid water could pool on a surface, 3 of them right there in the zone, and for the last 3 years, the most powerful space telescope ever constructed has been staring at those worlds. There is a moment in the history of astronomy that I return to often because it captures something essential about the way science actually works. Not the orderly progression of hypothesis to experiment to conclusion that gets printed in textbooks, but the messier, stranger, or human process of someone deciding to watch something no one else is watching, and finding something no one expected to find. That moment happened sometime in 2015, in the data stream of a small robotic telescope perched in the Atacama Desert of northern Chile, on a ridge called La Silla, under skies so dark and dry that the Milky Way casts a shadow on the ground. The telescope was called TRAPPIST, the Transiting Planets and Planetesimals Small Telescope, and it was, in the grand architecture of modern observatories, a modest instrument. Its mirror measured just 60 centimeters in diameter. For comparison, the primary mirror of the James Webb Space Telescope measures 6.5 meters across, more than 10 times larger. TRAPPIST was the kind of telescope that, in any other era, would have been operated by a university department and pointed at whatever was convenient. It was not the kind of instrument you would expect to announce the most significant exoplanet discovery of the 21st century. But the astronomer running it was Michaël Gillon, a Belgian researcher at the University of Liège, and Gillon had an idea that most of his colleagues considered a long shot at best and an eccentricity at worst. He wanted to look at ultra-cool dwarf stars, the smallest, dimmest, reddest stellar objects that can still sustain nuclear fusion, and look for planets transiting in front of them. The conventional wisdom held that these stars were too faint for precision photometry with a small telescope, too dim to reward the kind of careful attention Gillon was proposing, and probably too hostile with their violent magnetic activity and constant flares to host anything worth finding. The community's interest was directed elsewhere, toward sun-like stars, toward the Kepler field, toward the bright targets that everyone else was also watching. Gillon watched a star catalogued as 2 MASS J23062928-0502285. It sat into constellation Aquarius, 5 degrees south of the celestial equator, at a distance that would later be measured precisely by the Gaia satellite as 40.66 light-years from Earth. It was later given a more poetic designation, TRAPPIST-1. At the time, it was known primarily as an unremarkable, very dim, very red dot, an M8 spectral class ultracool dwarf with a surface temperature of 2566 Kelvin, which is cold enough for iron hydride molecules to condense in its outer layers, cold enough to turn the star the colour of a dying ember. It had a diameter only slightly larger than Jupiter's. Its total luminosity was approximately 0.055% that of our Sun. If it were placed at the centre of our solar system where the Sun currently sits, its light would be so dim that Earth would freeze solid. The planet Venus would be colder than Mars is today. None of that deterred Gillon, because the very dimness that made TRAPPIST-1 unattractive to most observers made it uniquely useful for his purposes. When a planet crosses in front of a small star, the fraction of starlight it blocks, the transit depth, is proportional to the square of the planet's radius divided by the square of the star's radius. The smaller the star, the deeper and more detectable that dip in brightness becomes. An Earth-sized planet transiting the Sun blocks roughly 84 parts per million of sunlight, a signal so small that detecting it requires extraordinarily sensitive instruments. an Earth-sized planet transiting TRAPPIST-1, a star only slightly wider than Jupiter, blocks roughly 1% of the star's light. That is a signal 12 times more detectable. The physics, in other words, was working in Gillon's favour if only he could persuade people that the star was worth watching in the first place. The light curves he collected in 2015 showed anomalies, periodic dimmings that didn't fit the noise profile, that repeated with uncanny regularity, that demanded an explanation. In May 2016, Gillon and his team published their first announcement in the journal Nature: 3 planets, all Earth-sized, all orbiting TRAPPIST-1 at distances far closer than Mercury orbits our Sun. The scientific community paid attention. Then, in February 2017, after a global campaign involving the Spitzer Space Telescope, the VLT at Paranal, the UK Infrared Telescope in Hawaii, and dozens of other instruments working in coordination, Gillon's team published again. Not 3 planets, 7. 7 Earth-sized worlds, all transiting, all in the same plane, all in circular orbits so close together that their orbital periods ranged from 1.51 days for the innermost world to 18.77 days for the outermost. For context, the innermost planet, TRAPPIST-1b, completes a full year in the time it takes our moon to go from new to full and back again. The outermost known planet, TRAPPIST-1h, completes its year in less time than it takes most people to complete a cycle of laundry. The press conference that NASA held on February 22, 2017 was unlike anything the agency had staged since the announcement of exoplanet discoveries in the 1990s. The hashtag trended globally within minutes. Astronomers who had spent careers patiently explaining to friends and family why the search for habitable worlds was a long-term project felt for the first time a tangible sense of proximity to the answer. Here were 7 worlds, all rocky, all the right size, 3 of them sitting precisely in the zone around their star where liquid water could exist on a planetary surface, and they were only 40 light-years away. A cosmic stone's throw, in a galaxy 100,000 light-years across. What no one was prepared for, or perhaps what everyone was quietly dreading, was the question that would dominate the next decade of research. Do any of those 7 worlds actually have an atmosphere? Because a rocky planet, in the habitable zone without an atmosphere, is not a habitable world, it is Mars. And we know with some precision what Mars looks like. It is a cold, irradiated, desiccated surface under a sky so thin that its atmospheric pressure at ground level is less than 1% of Earth's. Nothing drinks, nothing breathes, nothing lives on the surface of Mars, as far as we can tell, and the reason is straightforward. Its atmosphere was stripped away billions of years ago, and it never came back. The presence of an atmosphere is not a bonus feature for a habitable world. It is the entire story, and the story of what JWST has been finding at TRAPPIST-1, planet by patient planet, is one that the entire field of exoplanet science has been watching with a mixture of scientific excitement and slowly accumulating dread. 3 questions hang over everything that follows. First, why does the star itself present such a profound threat to the very atmospheres it might have helped create? Second, what has JWST actually found, from the innermost rocky worlds to the crown jewel of the habitable zone, TRAPPIST-1e? And third, the question that makes this more than astronomy, that makes it a question about whether we are alone in a universe of 700 sextillion stars. What does it mean if these worlds have nothing left? The answers are not yet complete, but they are further along than they were 3 years ago, and they are already changing the conversation. But before we can understand what JWST has found at TRAPPIST-1, we need to sit with an uncomfortable truth about the star itself, because the star is not a passive backdrop to this story. It is the central character. It is simultaneously the reason these worlds might be habitable and the reason they might not be. And the more we have studied it, the more the problem has come into focus as something almost paradoxical in its cruelty. TRAPPIST-1 is an M8 spectral class star, which places it at the extreme cool end of the red dwarf classification. Red dwarfs as a category make up approximately 73% of all stars in the Milky Way. They are the dominant form of stellar matter in the observable universe. And this is not a trivial point. If you want to count the planets in the galaxy that orbit in habitable zones, you must count the planets orbiting red dwarfs, because red dwarfs are so common that their habitable zone planets vastly outnumber the habitable zone planets of all Sun-like stars combined. The fate of life around red dwarfs is, in a very real sense, the fate of most life in the galaxy, if such a thing exists. This is why TRAPPIST-1 matters so much more than its modest size might suggest. It is not merely one system, it is a proxy for the largest class of stellar environments in the known universe. The trouble with TRAPPIST-1, and with ultra-cool red dwarfs generally, is a combination of factors that seem, at first examination, almost designed to produce inhospitable worlds. The first and most fundamental is what planetary scientists call the pre-main sequence luminosity problem, and it is, to my mind, one of the most underappreciated threats to life around small stars in the entire literature. When a star is young, before it settles into its long, stable hydrogen-burning phase on the main sequence, it is dramatically more luminous than it will be in maturity. For Sun-like stars, this pre-main sequence phase lasts only a few tens of millions of years, during which the habitable zone sweeps inward as the star dims. But the duration is short enough that planets have time to adjust. For TRAPPIST-1, the story is fundamentally different. Ultra-cool dwarf stars like TRAPPIST-1 spend up to 1 billion years in their pre-main sequence phase, contracting slowly and radiating far more energy than their adult selves will ever produce. During that billion-year adolescence, what is now the temperate habitable zone of TRAPPIST-1 was receiving radiation levels comparable to Venus's orbit around the Sun. The world's now sitting in the cool, pleasant equilibrium temperature range of the habitable zone spent hundreds of millions of years being cooked. Any primordial hydrogen atmosphere would have been photoionized and stripped by the star's extreme ultraviolet flux within that period. Any water oceans on the surface would have been heated into a runaway steam greenhouse effect, the steam rising into the stratosphere, where ultraviolet photons split the water molecules into hydrogen and oxygen, the hydrogen escaping to space, the oxygen potentially being absorbed by the crust or also escaping, leaving behind a dry, irradiated, likely magma-surfaced world. This process has a name, the steam atmosphere escape scenario, and it operates on timescales that are not speculative. They are derived from well-understood physics of atmospheric escape, combined with stellar evolution models that have been refined over decades. The pre-main sequence radiation environment of a system like TRAPPIST-1 would deliver to its habitable zone planets a total ultraviolet and extreme ultraviolet energy dose that is somewhere between 10 and 1,000 times greater than what the Earth received during its own formation. The innermost planet, TRAPPIST-1b, may have received enough early radiation to evaporate the equivalent of hundreds of Earth oceans of water before the star even settled down. This is the pre-main sequence problem. It is the first and most foundational threat, and it does not operate alone. Once TRAPPIST-1 finally settled onto the main sequence, around 7.6 billion years ago, based on current best estimates, making it nearly 2 billion years older than the solar system, it became the star it is today, dim, red, and deceptively stable-looking. But stable-looking is not the same as benign. TRAPPIST-1 is a fully convective star, meaning that energy transport throughout its entire volume is driven by the churning of hot plasma from core to surface, rather than the layered radiative zone that exists in the Sun's interior. Full convection drives intense, tangled magnetic field activity across the star's entire surface, producing powerful and frequent stellar flares. The Kepler K2 mission observed TRAPPIST-1 for 80 days and detected 42 distinct flares during that period, roughly one every 2 days, and those were only the ones large enough to register clearly. The actual flare rate, including microflares and nanoflares below the detection threshold, is almost certainly higher. Each flare releases a burst of ultraviolet and X-ray radiation, and some of the more powerful events also drive coronal mass ejections, enormous ejections of stellar plasma travelling at hundreds of kilometers per second, slamming into the magnetospheres or surfaces of any nearby planets. Here is where the atmospheric erosion problem compounds the pre-main sequence and damage. Even if the TRAPPIST-1 planets somehow retained or rebuilt atmospheres during the star's long early period of quiescence, those atmospheres would be continuously eroded by the flare radiation and particle flux of the mature star. Whether a planet can resist this erosion depends on a combination of factors: the strength of its magnetic field, which depends on whether the planet has a molten, convective iron core still generating a dynamo, the composition of its crust, which affects whether volcanic outgassing can replenish lost gases, and critically, the initial volatile inventory of the planet: how much water, carbon dioxide, nitrogen, and other atmospheric gases it started with. For the inner, hotter TRAPPIST-1 planets, models suggest the combination of early high radiation and continuous mature star flaring has likely eroded any significant primordial atmosphere entirely. The outer planets might have fared better, but their situation is still far from guaranteed. There is, however, one reason not to despair entirely, and it comes from the density measurements. Because the TRAPPIST-1 system is a transiting system, with all 7 planets crossing in front of the star as seen from Earth, we have been able to measure not only the planets' radii from the transit depths, but also their masses from the gravitational perturbations they exert on each other's orbits as they dance through their resonant chain. And when you divide mass by volume, you get density, a measurement that tells you, in broad strokes, what a planet is made of. The densities of the TRAPPIST-1 planets are consistently lower than you would expect for purely rocky worlds built from iron and silicate rock. A pure rocky planet at these masses should have a density of roughly 5,000 to 6 zeros kilograms per cubic meter. Several of the TRAPPIST-1 planets come in noticeably below that. The implication is that they contain significant amounts of lower density material, and the most probable candidate is water. Some estimates place the water content of the outer TRAPPIST-1 planets at between 5% and 50% by mass. Earth, by comparison, has a water content of approximately 0.02% by mass. If those density measurements are telling us what we think they are, these worlds began their lives as extraordinarily water-rich objects, oceanic worlds, perhaps, built from material that formed far from their current positions and migrated inward. The water that was lost to early atmospheric stripping may have been, in the outer planets at least, a fraction of a vast primordial ocean. But that is a story about the past. The question that JWST is trying to answer is about the present, about what survives today at this moment in the system's 7.6 billion year history. And to understand what JWST has found, we need to understand one more piece of architecture: the resonant chain, the orbital clockwork that makes this system unlike almost anything else we have discovered, and that raises one of the strangest habitability questions in modern planetary science. The 7 TRAPPIST-1 planets orbit in what astronomers call a resonant chain, a gravitational arrangement in which the orbital periods of adjacent planets form simple integer ratios. For every 8 orbits of TRAPPIST-1b, TRAPPIST-1c completes exactly 5. For every 5 orbits of TRAPPIST-1c, TRAPPIST-1d completes 3. The pattern continues through the system, each planet locked in gravitational conversation with its neighbours, tugging at each other in precisely rhythmic ways. This is not a coincidence. Resonant chains form when a planetary system migrates through a protoplanetary disk in a specific way, with planets shepherding each other into these locked configurations as they travel inward. The system looks not like a random outcome, but like a musical composition. Its periods following ratios of 8-5, 5-3, 3-2, 3-2, 4-3, and 3-2 from innermost to outermost. Playing those ratios as sound frequencies produces, quite literally, a chord. The TRAPPIST-1 system makes a kind of music. The resonant chain has direct consequences for habitability that are only partially understood. Tidal forces, the same gravitational kneading that makes Io the most volcanically active body in the solar system, may be doing significant work on the inner TRAPPIST-1 planets. As the planets pull on each other and their orbits respond, Their interiors are squeezed and stretched, generating heat. That heat could be enough, in some models, to drive sustained volcanic activity even on planets whose iron cores have long since frozen solid. Volcanic outgassing, the process by which a planet continuously vents gases from its interior into a new atmosphere, could, in principle, replenish an atmosphere that flare erosion is steadily stripping away. It is a race between destruction and renewal, and the outcome depends on numbers, eruption rates, flare intensities, gas molecular weights, magnetic field strengths, that we are only now beginning to constrain. But we were about to get real data. The James Webb Space Telescope had been launched on December 25, 2021, deployed at the second Lagrange point 1, 5 million kilometers from Earth, cooled to its operating temperature of 6.4 Kelvin above absolute zero, and trained on the universe. TRAPPIST-1 was on its target list from day one, and what the telescope found when it finally began speaking was more complicated and more sobering than even the pessimists had expected. The first JWST results from TRAPPIST-1 arrived in the spring of 2023, and they arrived not with fanfare, but with the quiet, precise authority of a measurement that changes a conversation permanently. They concerned the two innermost planets, TRAPPIST-1b and TRAPPIST-1c. Neither of these worlds sits in the habitable zone. Planet B orbits so close to its star that it receives radiation equivalent to roughly 4 times what Earth receives from the Sun, and Planet C orbits slightly farther out, but is still well within the inner edge of anything any climate model would consider temperate. They were not the planets that had captured the public imagination, but they were the planets that JWST could most easily study first, because their proximity to the star means they transit more frequently, giving the telescope more opportunities to collect data per unit of observing time. They were the first evidence. They were the beginning of a verdict. The technique JWST used for the inner planets was thermal emission measurement, specifically through secondary eclipse observations. Here is how it works. When a planet passes behind its star, an event called secondary eclipse, the telescope loses the planet's contribution to the combined star plus planet light signal. By measuring the brightness of the system during the eclipse, when only the star is visible, and comparing it to the brightness just before and after the eclipse, when both the star and the planet's day side are contributing, astronomers can calculate the brightness temperature of the planet's day side. That temperature is then compared to what you would expect for a bare rock at that distance. A world with no atmosphere to redistribute heat, and for a world with various possible atmospheric compositions. If a planet has a substantial atmosphere, it will redistribute heat from its permanent day side to its permanent night side, moderating the day side temperature compared to what a bare rock would reach. If the dayside temperature is exactly what you would expect for a bare, airless rock, the implication is stark. For TRAPPIST-1b, the JWST MIRI instrument measured a dayside brightness temperature of approximately 508 Kelvin, 235 degrees Celsius, during observations published in Nature in May 2023. The expected temperature of a bare dark rock at that orbit would be around 400 Kelvin, while the expected temperature of a rock with a high albedo, a reflective surface covered in pale minerals, would be slightly lower. A planet with a thick atmosphere circulating heat around the globe would be significantly cooler on the day side. The measurement of 508 Kelvin was not merely consistent with a bare rock, it was almost perfectly, uncomfortably consistent with a bare rock. The team published their result with characteristic scientific restraint. The most straightforward interpretation, they wrote, was that there was little or no planetary atmosphere redistributing radiation. They hadn't proven absence. They had found no evidence of presence, which in science is a different but still powerful statement. For TRAPPIST-1c, the picture was only marginally less stark. Published in Nature in June 2023, the JWST MIRI thermal emission data showed a dayside temperature of approximately 380 Kelvin, about 107 degrees Celsius, which is actually cooler than a bare dark rock at that orbit would reach. suggesting some reflectivity from either a thin cloud cover or a pale, mineral-rich surface. This result was initially interpreted with a measure of cautious hope. The temperature was inconsistent with a thick, Venus-like CO2 atmosphere, but perhaps consistent with something thin and reflective. The team's conclusion was that no thick carbon dioxide atmosphere existed on TRAPPIST-1c, and that the planet's relatively volatile pore formation history was suggested by the result. The absence of a thick CO2 atmosphere implied the planet had started with less than the equivalent of 9.5 Earth oceans of water, but the result did not rule out a thin or partial atmosphere entirely, and that narrow window remained open for the time being. Then, in April 2026, Gillon himself, the man who had discovered the system, led a team that published a new and definitive thermal phase curve study in Nature Astronomy. This was not a snapshot measurement of the secondary eclipse alone. This was 60 hours of continuous observation with JWST, tracking both TRAPPIST-1b and TRAPPIST-1c through complete orbits, mapping the temperature distribution across each planet's entire surface, from the scorching day side to the freezing night side. The temperature contrast they measured was not merely large, it was total. TRAPPIST-1b registered a dayside temperature of approximately 200 degrees Celsius, while its night side plunged below negative 200 degrees Celsius. That is a temperature swing of 400 degrees across a single planet. TRAPPIST-1c showed a similar pattern. No atmosphere capable of transporting meaningful heat from dayside to nightside could produce that pattern. The conclusion, stated now with considerably more confidence than the 2023 papers, was that neither TRAPPIST-1b nor TRAPPIST-1c has a detectable atmosphere. They are bare rocks. They are hot on one side and frigid on the other, with nothing in between. This is what I would call the thermal divide problem, and it is about as stark a piece of evidence as the field of atmospheric characterization produces. A tidally locked planet without an atmosphere is a binary world. Roasting dayside, frozen nightside, no circulation, no moderation. The difference in temperature between the equator facing the star and the hemisphere that has never seen sunlight at all is limited only by the thermal inertia of the rock itself. It is a world where sunrise and sunset mean nothing, because they never happen, and where the geology of one hemisphere and the other could, in principle, be as different as the surface of Mercury's scorched dayside versus its permanently shadowed pole craters, which harbour water ice at their bottoms. The TRAPPIST-1b and TRAPPIST-1c thermal measurements are the most precise temperature maps ever made of rocky exoplanets, and they are telling a story that is not, at this moment, an optimistic one. But here the open questions multiply, because the inner planets were never the prize. They were the calibration. They were the warm-up act before the telescope turned to the worlds that actually matter, the 3 planets in the habitable zone, designated D, E, F and G, the worlds where liquid water is physically possible, where the physics allows for the conditions in which life as we know it can emerge. And among those 4, one planet, TRAPPIST-1e, has attracted more concentrated scientific attention than any Earth-sized planet in the known galaxy beyond our own solar system. There is also a deeper complication that the thermal emission measurements of the inner planets have introduced, and it is one that has not received the public attention it deserves. Even for the inner worlds, JWST is not seeing the planets directly. It is seeing the planets through the turbulent, spotted, flare-active atmosphere of TRAPPIST-1 itself, and the star is proving to be a far more difficult foreground than anyone had hoped. This is the stellar contamination problem, a second, compounding challenge sitting atop the already demanding physics of measuring a rocky planet's atmosphere from 40 light-years away. And it is, in its way, as important as any of the atmospheric findings themselves. Because if we cannot reliably distinguish the spectral signal of a planetary atmosphere from the noise introduced by a magnetically hyperactive red dwarf star, then even a genuine atmospheric detection becomes ambiguous. And JWST, for all its extraordinary engineering, is not immune to this problem. It sees the universe with more precision than any telescope in human history, and it is still not enough. Not quite yet. There is a paradox at the heart of the TRAPPIST-1 investigation that took years to fully appreciate, and which the JWST data have now brought into sharp focus. The instrument is more than capable enough to detect molecular signatures in the atmosphere of a rocky exoplanet. Its spectral resolution and sensitivity are, by significant margins, superior to anything previously deployed in space. The problem is not the telescope. The problem is the star. The star it must look through to reach the planet is not a clean, uniform background light source. It is an active, spotty, magnetically tormented red dwarf that is simultaneously the reason these planets are detectable, and the reason they are so fiendishly difficult to characterize. To understand the stellar contamination problem properly, you need to understand what JWST is actually doing during a transmission spectroscopy observation. When TRAPPIST-1e, or any of the other planets, passes in front of the star, the telescope measures how the planet's apparent size changes with wavelength. A thick atmosphere absorbs more light at wavelengths matching the absorption bands of its constituent molecules, making the planet appear larger at those wavelengths. The difference in apparent size across wavelengths, the transmission spectrum, is the atmospheric fingerprint for an Earth-like atmosphere on an Earth-sized planet around a Sun-like star. That signal would be impossibly small to detect with current technology. But TRAPPIST-1 is so much smaller than the Sun that the signal from even a thin atmosphere on an Earth-sized planet is amplified to the point of potential detectability in the range of tens to hundreds of parts per million, depending on the atmosphere's composition and scale height. However, the star's surface is not uniform. TRAPPIST-1 has cool dark spots, analogous to sunspots on our Sun, but produced by the star's intense, fully convective magnetic field, as well as bright, hot faculae, magnetically elevated regions that are hotter and brighter than the surrounding photosphere. When the planet transits, it crosses in front of some combination of these features, and the spectral characteristics of the star's surface at the transit chord are different from the spectral characteristics of the disk-integrated star that JWST measures during the out-of-transit baseline. This mismatch produces what looks, in the transmission spectrum, exactly like a molecular absorption feature, a spurious signal that can mimic the presence of atmospheric gases that are actually absent, or mask the presence of real atmospheric signals beneath a wash of stellar noise. This is the stellar contamination signal, and for TRAPPIST-1, it can be an order of magnitude larger than the actual planetary atmosphere signal the team is trying to detect. The first JWST near-spec prism transmission spectrum of TRAPPIST-1e, published by Anna Glidden and collaborators at MIT, Stanford, Johns Hopkins, and the University of Arizona in September 2025, was a landmark result, not because it definitively detected an atmosphere, but because it characterized the stellar contamination so precisely that it advanced our ability to correct for it. Glidden's team developed a novel observational strategy. By observing TRAPPIST-1e across 4 separate transit events and looking for signals that were consistent from visit to visit, they could separate the planetary contribution, which should be stable since the planet's atmosphere does not change between visits, from the stellar contribution, which varies unpredictably from day to day as spots and faculae evolve across the star's surface. Anything variable from visit to visit was almost certainly stellar in origin. Anything stable across all 4 visits was almost certainly planetary. What they found after applying this correction was a transmission spectrum that ruled out several atmospheric scenarios with meaningful confidence. A thick, hydrogen-dominated atmosphere was ruled out. Such an atmosphere would produce a transmission spectrum signal of thousands of parts per million, which would have been clearly detectable despite the stellar noise was not seen. A thick carbon dioxide atmosphere like Venus's was inconsistent with the data. A Mars-like thin CO2 atmosphere was also disfavoured. What remained, after eliminating these scenarios, was a space of possibilities that still includes 2 very different futures for TRAPPIST-1e. The first is a bare, airless, rocky surface, no atmosphere at all. The same story as the inner worlds, the same thermal divide, the same irradiated rock. The second, and this is the possibility that makes every researcher in the field pause before speaking, is a secondary, nitrogen-rich atmosphere similar in composition to Earth's own, or perhaps to Saturn's moon Titan, which has a thick nitrogen atmosphere with traces of methane. These two scenarios, diametrically opposed in their implications for life, remain consistent with the current JWST data. The telescope has narrowed the field. It has not yet delivered the verdict on the planet that matters most. This 50-50 ambiguity, this scientific knife edge, has a specific cause, and that cause is exposure time. 4 transit observations of TRAPPIST-1e are, as Gillon explicitly stated, not enough to achieve the signal-to-noise ratio needed to definitively distinguish between an airless world and a thin nitrogen-rich atmosphere. The signal from a secondary atmosphere, at the scale heights expected for a nitrogen-dominated world, is roughly 15 to 30 parts per million in the transmission spectrum. That is not much larger than the current measurement uncertainties. To push through that uncertainty, to achieve the statistical confidence needed to say definitively whether TRAPPIST-1e has an atmosphere or not, the team needs more transits. Significantly more, which is why the JWST DREAMS program, deep reconnaissance of exoplanet atmospheres using multi-instrument spectroscopy, has been awarded 130 hours of JWST time to observe TRAPPIST-1e and several other planets in the system. That 130-hour allocation represents one of the largest single-target observing programs in JWST's history. 15 additional transits of TRAPPIST-1e have already been scheduled, and those observations are expected to reduce the atmospheric uncertainty by a factor of 2 to 3, potentially crossing the threshold of detection or non-detection before the end of 2026. There is a number worth sitting with here: 130 hours. The most capable space telescope in human history, a $10 billion instrument that took 25 years to design and build, costing roughly $1 million per hour of operating time, based on the lifetime mission budget. And the team needs 130 of those hours on a single star system. Not because the telescope is inadequate, because the physics of a nitrogen-rich atmosphere on a planet 40 light-years away is genuinely right at the edge of what can be detected with current technology. We are pushing this instrument to its absolute physical limit. This is not a story of technological triumph over a scientific problem. This is a story of a scientific problem that is barely within reach of a question that sits at the very edge of what our civilization can currently ask of the universe. But while the final verdict on TRAPPIST-1e awaits its full complement of transit observations, the intermediate planets, TRAPPIST-1d and TRAPPIST-1f and g, have also been speaking, and what they are saying does not simplify the picture. TRAPPIST-1d, which sits at the inner edge of what some models place as the habitable zone, was studied in 2024 and 2025 with JWST NIRSpec and MIRI instruments, and the results were published in early 2025 by a European-led team coordinated through the James Webb partnership. Their conclusion was that TRAPPIST-1d shows no evidence of an Earth-like thick atmosphere. The dayside temperature profile was consistent with either a bare rock or a planet with extremely thick, high-altitude clouds, a scenario sometimes called a thick, reflective cloud deck, or a world with a thin, low-density atmosphere similar to what remains on Mars today. The planet is not bare in the same clear-cut way as TRAPPIST-1b, but neither is it wearing the kind of thick atmospheric blanket that would make it a comfortable place to stand. It exists in an intermediate zone of ambiguity, its atmospheric status genuinely uncertain in a way that requires more observations to resolve. The outer planets, TRAPPIST-1f and TRAPPIST-1g, have received less JWST attention to date, partly because their longer orbital periods mean fewer transit events per year, and hence slower accumulation of spectral data, and partly because the community has focused its limited telescope time most aggressively on TRAPPIST-1e, which occupies the most unambiguously central position in the habitable zone. But the outer planets are not irrelevant to the story. Their density measurements suggest they may be the most volatile rich of the 7 worlds, potentially harbouring the largest initial water inventories. If any planet in the TRAPPIST-1 system has retained a thick atmosphere against the star's ravages, the outer worlds are the most likely candidates. They receive less radiation. They have larger volatile reservoirs. The surface gravity of TRAPPIST-1g is roughly 1.12 times Earth's, which means its escape velocity is slightly higher, making it marginally harder for atmospheric gases to be lost to space. These are small advantages, but in the economics of atmospheric retention against relentless stellar erosion, small advantages can accumulate over billions of years into the difference between a world with oceans and a world with dust. And yet, the question that defines all of this, the question that makes the TRAPPIST-1 campaign the most consequential observational program in the history of exoplanet science, is not really about any single planet. It is about the class. It is about whether rocky planets around red dwarf stars can, as a general rule, retain the atmospheres needed for life. Because if TRAPPIST-1e is bare, if even the most intensively studied habitable zone rocky planet around the most amenable nearby red dwarf comes back as an airless rock, then we are looking at a pattern, not an exception. And that pattern has implications that reach far beyond one solar system 40 light-years from home. I want to tell you about a man who spent years justifying something that his colleagues thought was, at best, a marginal investment of scientific resources, and who discovered the most celebrated planetary system of the modern astronomical era, not because he was better equipped than everyone else, or because he had access to resources others lacked, but because he asked a different question in a different direction and was stubborn enough to keep asking it. Michaël Gillon was born in Liège, Belgium, and he came to astronomy through a path that was somewhat circuitous. He had originally studied chemistry before pivoting to astrophysics, which is perhaps why he retained a chemist's instinct for following the data even when it didn't fit the expected narrative. He completed his doctorate at the University of Liège and joined the faculty there as a researcher focused on exoplanet transits, specifically on using small, affordable telescopes to detect and characterize planetary transits around faint stars. This was, in the mid-2000s, not the mainstream of exoplanet science. The mainstream was the Kepler Space Telescope, which was being designed and built to stare at a single field of stars, all sun-like, all bright, all well understood, and count planetary transits by the thousands. The statistical approach, the industrial scale approach, the approach that would eventually produce a catalogue of over 5,000 confirmed exoplanets, was the one receiving the attention, the funding, and the prestige. Gillon was interested in something smaller and, in his view, more fundamentally tractable. Rather than discovering thousands of exoplanets orbiting stars too far away to ever study in detail, he wanted to find a handful of planets orbiting nearby, faint, small stars that could be studied with extraordinary depth. The trade-off was straightforward in theory. Ultra-cool dwarf stars were difficult, faint targets that required long integration times even for photometry, but the transit signals they produced from Earth-sized planets were so much deeper than those around Sun-like stars that even a small telescope could detect them. If you accepted the difficulty of the target, you gained an enormous leverage advantage in the detectability of the signal. He proposed the TRAPPIST telescope in the late 2000s. The instrument was built and installed at La Silla Observatory in Chile, operated robotically, and initially used to monitor a survey list of about 50 nearby ultra-cool dwarf stars. The proposal's funding application was reviewed and approved, but not without friction. The concern, articulated by several reviewers and colleagues, was that even if planets were found around such difficult targets, characterizing them, understanding their atmospheres, their compositions, their potential habitability, would be so technically demanding with foreseeable instruments that the investment might not pay off in any reasonable scientific timescale. Gillon disagreed with the quiet, persistent confidence of someone who had done the calculation carefully and trusted the numbers. He knew that a deep transit on a small red dwarf was not merely detectable. It was characterizable with the next generation of space telescopes, specifically the James Webb Space Telescope, which was then in advanced development. He was working backwards from a future capability, designing a discovery campaign for an instrument that didn't exist yet. This is the part of the story I find most compelling. In a field where most observational programs are designed around the capabilities of existing instruments, Gillon was building a discovery strategy for a telescope that would not launch for more than a decade. He was betting not only that his survey would find planets, but that the next generation of technology would be ready and able to study them before his career ended. That is not a gamble in the pejorative sense. It is engineering foresight of a rare and genuinely admirable kind. The bet required everything to go right. The TRAPPIST telescope had to find transiting planets. Those planets had to be close enough to Earth. JWST had to be launched on schedule and perform to specifications, and the observational programs had to be awarded telescope time in a competitive allocation process against hundreds of other worthy scientific proposals. Everything went right. Almost. The TRAPPIST telescope detected anomalies in the light curve of 2 MSS J230629280 05022885, the star that would become TRAPPIST-1 in late 2015. The dimmings were periodic, shallow by comparison to a Jupiter transit, but clearly real, and they repeated at intervals of a day and a half, then with a slightly longer period that turned out to be a second planet. Gillon and his team, including collaborators in Belgium, Switzerland, France, the UK and the United States, began coordinating a global observational campaign, pulling in telescope time from Spitzer from the ESO VLT, from ground-based instruments in Chile, South Africa, Morocco, Hawaii and Spain. For weeks, the team worked at the pace that major discoveries demand, intensely, almost without sleep, cross-checking the photometry, the spectroscopy, the stellar characterization, looking for the alternative explanations that must be systematically eliminated before a discovery claim can be made with confidence. Gillon has spoken in interviews about the moment he became convinced the signals were real. Not one moment, but a series of accumulating moments over several weeks, each new data point tightening the case and simultaneously raising the stakes. The February 2017 announcement, 7 planets, 3 in the habitable zone, the nearest known system of potentially Earth-like worlds, was the result of that campaign, and it was received with a level of public and scientific enthusiasm that few astronomical discoveries outside the Apollo era had generated. Gillon was quoted everywhere. His work was cited in news coverage globally. The word landmark appeared in more press releases than any one person could track. But here is the part that doesn't appear in the press releases. In the years after the announcement, as JWST began collecting data on TRAPPIST-1 and the early results began returning, TRAPPIST-1b, bare rock, TRAPPIST-1c, no significant CO2 atmosphere, TRAPPIST-1d, uncertain but not encouraging, Gillon was not a passive observer of the dismantling of his discovery's most hopeful implications. He was an active participant in the measurements themselves. The April 2026 thermal phase curve paper that provided the most definitive evidence yet of atmospheric absence on both TRAPPIST-1b and TRAPPIST-1c. The paper published in Nature Astronomy that concluded with the precision of 60 hours of JWST data that neither inner planet has a detectable atmosphere, was authored by Gillon himself. He led the team. He ran the analysis. He published the result that his own discovery was, in its innermost 2 planets at least, a system of bare rocks. There is something in that which I have thought about for quite a while. The willingness to be the person who tells the truth about the thing you love most, with full awareness that the truth may be disappointing, is a form of scientific integrity that doesn't get celebrated the way discoveries do, but which is arguably more important. Any scientist can be enthusiastic about their own positive results. Far fewer can be trusted to lead the charge on the measurement that complicates or contracts those results. Gillon is a member of that smaller, more valuable category, and the fact that he is also the person who has been awarded more JWST time than almost any other investigator to continue probing TRAPPIST-1, including the 130-hour DREAMS program observations of TRAPPIST-1e, suggests that the scientific community understands this. They are trusting the person most invested in finding an atmosphere to be the person most rigorously testing for its absence. The result, if it eventually comes, of a confirmed nitrogen-rich atmosphere on TRAPPIST-1e with its hints of methane, its suggestion of a secondary atmosphere rebuilt from volcanic gases after the primordial one was stripped away, will be the capstone of Gillon's career. It will be the confirmation that the bet was not merely right about the planets, but right about what the planets were. And if TRAPPIST-1e comes back bare, if the 130-hour investment returns a flat, featureless spectrum that rules out all but the thinnest of atmospheres, then Gillon will publish that result too, with the same rigour, the same transparency, the same commitment to the universe as it actually is, rather than the universe as we would prefer it to be. I find it remarkable that the same man who spent years watching a star nobody else was watching is now the person most carefully watching to find out whether those worlds are empty. The discovery is his. The reckoning, it turns out, will also be his. There is one more dimension to this human story that deserves mention. Gillon's project was named after TRAPPIST, the Transiting Planets and Planetesimals Small Telescope, which is itself an acronym constructed with particular care, because TRAPPIST is also the name of a monastic order of Catholic monks, the Trappists, famous for their vows of silence and their beer. Gillon, a Belgian who studied chemistry and chose to spend his career watching the sky, through a modest telescope in the desert, named his instrument after an order of silent observers, and then used it to make one of the loudest discoveries in recent scientific history. Whether that irony was intentional or accidental, I have never managed to find out. But I rather hope it was deliberate. The hunt for an atmosphere on TRAPPIST-1e continues. The observations are scheduled, the analysis is underway, and somewhere in Liège, the man who started this watching the data arrive at his terminal is still watching. Let us step back from the photometry, from the spectral residuals, from the parts per million signal buried in the JWST data, and consider what is actually at stake here, not just for TRAPPIST-1, but for the entire question of whether the universe is populated or empty. There are approximately 400 billion stars in the Milky Way. Of those, roughly 70 to 73% are red dwarfs, M-type stars of varying sizes and temperatures, from the warmest and most sun-like at the M0 boundary, to the ultra-cool M8 and M9 dwarfs like TRAPPIST-1 at the far cool end of the classification. If you include K-type stars, which are intermediate between M-type and G-type, sun-like stars, and share several of the hostile properties of red dwarfs for habitability purposes, the fraction of stars that are cooler and smaller than the Sun rises above 90%. The sun-like G-type stars that we tend to think of as the natural hosts for life, the stars like our own with their stable UV environments, their roughly sun-scale luminosities, their well-behaved flare rates, make up only about 7% of all stars in the galaxy. The universe has overwhelmingly decided to build red dwarfs. This has enormous implications for any calculation of the prevalence of life in the universe. The Drake equation, formulated by Frank Drake in 1961 as a framework for estimating the number of communicable civilizations in the galaxy, includes a term for the fraction of stars with planetary systems, a term for the fraction of those systems with planets in the habitable zone, and a term for the fraction of those habitable zone planets on which life actually emerges. If red dwarf habitable zone planets systematically lack atmospheres, if the physics of stellar radiation and early atmospheric stripping makes the rocky worlds around M-type stars structurally uninhabitable, then the effective habitable fraction of the galaxy collapses dramatically, not because there are fewer planets in habitable zones, but because the planets that exist in habitable zones around the most common type of star cannot sustain the conditions required for life as we understand it. This is the stakes ladder at its highest rung, and it is not science fiction. It is a logical consequence of what the JWST TRAPPIST-1 observations are beginning to suggest. If we find that TRAPPIST-1b is bare, confirmed, as the thermal phase curves strongly suggest, and TRAPPIST-1c is bare, and TRAPPIST-1d has at best a thin, almost negligible atmosphere, and even TRAPPIST-1e, the best candidate in the best studied system of nearby potentially habitable worlds, turns out to be an airless rock, then we are not looking at an unlucky system. We are looking at a pattern that likely extends to red dwarf habitable zones throughout the galaxy. A great filter, a concept introduced by Robin Hanson in 1998 to describe whatever obstacles lie between simple chemistry and interstellar civilizations, may not be a biological event, may not be a technological catastrophe, may not be a war or a plague or a climate collapse. It may be as simple and merciless as the ultraviolet environment of a red dwarf star during its first billion years. It may be the pre-main sequence luminosity problem operating at galactic scale, stripping atmospheres from rocky habitable zone planets around the most common stars before life has any opportunity to begin. I want to be careful here, because this conclusion, even stated tentatively, carries enormous weight, and the evidence is not yet sufficient to state it definitively. The JWST data on TRAPPIST-1 is incomplete. The outer planets have not been fully characterized. TRAPPIST-1e is still ambiguous, and even within the TRAPPIST-1 system, there are models that predict atmospheric survival under specific conditions. If the planet has a magnetic field strong enough to deflect the charged particle component of stellar flares, if volcanism has replenished the atmosphere from below, if the initial water inventory was enormous enough that even after the pre-main sequence phase, some residual volatile layer remained. These are not impossible scenarios. They are physically plausible and scientifically legitimate. The story is not over, but the story is also not the one that was told at the 2017 press conference. The narrative of 7 potentially habitable worlds, 3 in the Goldilocks zone, the most promising system for life beyond Earth, that narrative has been progressively, systematically complicated by the actual data, not destroyed, complicated. The TRAPPIST-1 system remains the most scientifically valuable system of rocky worlds ever identified, because even if none of the planets have habitable atmospheres today, the question of why they don't, what that means for red dwarf habitability generally, is one of the most important questions in modern astrophysics. A negative result of sufficient precision is still a profound result. Knowing that the cosmic atmosphere erosion problem operates the way the models predict is not a disappointment. It is a discovery. It closes one door on one version of the universe we might have lived in, and it points toward the doors that remain open. Those remaining open doors are worth naming explicitly. First, the possibility of subsurface habitability. Europa, Enceladus, Ganymede, and Titan in our own solar system have demonstrated that liquid water, and in the case of Enceladus, actively erupting organic chemistry, can exist beneath ice shells on worlds far outside any conventional habitable zone definition. The TRAPPIST-1 planets, despite losing their surface atmospheres, may have retained internal heat through tidal heating, the gravitational kneading of their resonant chain, the same mechanism that drives Io's volcanism. If TRAPPIST-1d, EF, or G has a frozen surface above a tidally maintained subsurface ocean, then the concept of habitability on these worlds does not require an atmosphere at all. Life does not read the textbook definition of the habitable zone. Life finds thermal gradients and liquid water wherever they exist. Second, the possibility that our models of atmospheric erosion around red dwarfs are wrong in a specific and important way. Current models of stellar wind particle flux, coronal mass ejection frequency, and XUV photon energy input to the TRAPPIST-1 planets are built on incomplete observations of the star's high-energy environment, because the X-ray and extreme ultraviolet luminosity of TRAPPIST-1 is genuinely difficult to measure precisely. If the actual XUV environment of the mature star is significantly lower than current estimates, if TRAPPIST-1's magnetic field topology traps more coronal mass ejections than models predict, as some simulations suggest is possible, then the atmospheric erosion rates on the outer planets could be low enough that secondary atmospheres, rebuilt from volcanism, have survived. This is a genuine scientific uncertainty, not wishful thinking, and it is one that ongoing observational campaigns with X-ray telescopes and the newly operational instruments of the extremely large telescope will help resolve. Third, the possibility, which Gillon himself has discussed publicly, that even if TRAPPIST-1e has no atmosphere today, it might have had one in the past, and that the geological or chemical record of that past atmosphere might be encoded in the planet's spectral characteristics in ways we have not yet learned to read. The field of exoplanet geology is in its absolute infancy. We are at the stage of trying to determine whether a given planet has any atmosphere at all. We are not yet at the stage of reading its geological history from its current mineral composition. But in principle, the transit spectrum of a bare rocky planet is not a blank page. The mineralogy of its surface, the kinds of silicates, oxides and carbonates exposed at the crust, leaves spectral fingerprints in the mid-infrared that JWST can in principle detect. Reading those fingerprints to reconstruct past atmospheric history is a project that will define the next decade of terrestrial exoplanet science. Meanwhile, there is a consequence of the TRAPPIST-1 findings that has begun to reshape how astronomers plan the next issue of observatory programs, and it is a consequence that deserves its own space in this story. The assumption that underlies most biosignature detection strategies is that if a planet is in the habitable zone of its star and has an atmosphere, the atmosphere's composition might contain biosignatures, gases like oxygen, ozone, nitrous oxide, or methane in disequilibrium combinations that can only be maintained by ongoing biological production. This assumption requires the atmosphere to exist. If red dwarf habitable zone planets systematically lack atmospheres, then the entire biosignature detection program built around transmission spectroscopy of those planets needs to be fundamentally reassessed, not abandoned, reassessed. Either we must work harder to find the exceptional red dwarf systems where atmospheres have survived, which requires much longer observational campaigns to characterize each candidate individually, or we must turn our attention more aggressively toward the atmospheres of habitable zone planets around more sun-like stars, which are harder to detect but whose stellar environments are less hostile. The TRAPPIST-1 observations have, in other words, done something that science occasionally does at its most productive. They have not merely answered a question, but have reframed the next 10 questions, and sitting at the centre of that reframing, answering some questions with uncomfortable finality while leaving others wide open, is a 6.5-metre mirror orbiting 1.5 million kilometres from Earth, gathering photons that left a star 40 light-years away, and returning to us in the form of spectra and brightness curves, the most detailed portrait of another solar system that humanity has ever assembled. Science that appears in press releases is almost without exception cleaner and more certain than the underlying data deserves. This is not dishonesty. It is the inevitable compression of nuance that occurs when researchers communicate with a public that has neither the time nor the technical background to engage with error bars, systematic uncertainties, model degeneracies, and the elaborate chain of assumptions that lie between a raw photon count and a headline about a potentially habitable world. What follows is an attempt to do something that long-form science communication rarely does well. To sit honestly with the complications, the genuine uncertainties, and the specific technical problems that make the TRAPPIST-1 story more qualified and more interesting than any 10-word summary can capture. The most important complication in the entire JWST TRAPPIST-1 program is one that the researchers themselves have been admirably forthcoming about, and which has become, in a short time, one of the defining methodological challenges of terrestrial exoplanet spectroscopy. The problem of stellar contamination is not merely a background nuisance to be subtracted. It is a fundamental limitation of the transmission spectroscopy technique as applied to active red dwarf stars, and its severity was not fully appreciated before JWST began returning data. Here is the technical core of the problem. When a planet transits TRAPPIST-1, it covers a chord of the stellar disk. The spectrum of that chord, the light being blocked by the planet, is not the same as the average spectrum of the entire stellar disk. If the transit chord happens to cross a cool star spot, the blocked light is redder and dimmer than average. If it crosses a hot facula, the blocked light is bluer and brighter. The difference between the spectrum of the chord and the spectrum of the disk produces a spurious signal in the transmission spectrum, a signal that has nothing to do with the planet's atmosphere, but that looks, spectrally, very similar to molecular absorption features. For TRAPPIST-1b, the first JWST NIRSpec transmission spectroscopy paper, published in late 2024 and based on observations led by Espinosa and collaborators, found that the stellar contamination signal was not merely comparable in magnitude to any possible atmospheric signal. It was dominant. The stellar contamination was, in places, 4 to 10 times larger than the expected atmospheric signal from even a substantial atmosphere on the planet. The contamination had to be modelled, characterised, and subtracted before any claim about the planet's atmosphere could be made. And the uncertainty in that subtraction propagated directly into the atmospheric constraints. Glidden's approach for TRAPPIST-1e, using multiple transit visits and looking for the visit invariant residual, was precisely designed to address this problem, and it represents a genuine methodological advance. But the advance has a cost. It requires more telescope time. 4 visits give you a rough separation of planetary signal from stellar noise. 15 visits give you something approaching a reliable atmospheric constraint. It is not clear whether even 15 visits will be enough to push the TRAPPIST-1e result below the ambiguity threshold for a thin nitrogen-rich atmosphere, because the visit-to-visit variability of TRAPPIST-1 appears to be significant enough that even with a stellar activity model, the residual stellar noise is substantial. Some team members, speaking informally at conferences during 2025, suggested that a definitive atmospheric detection or non-detection for TRAPPIST-1e might require the equivalent of 30 to 40 transit observations, more than the entire DREAMS program has currently been allocated. This is a statement about the limits of current technology applied to this specific problem, and it is worth examining carefully rather than dismissing. It does not mean the problem is insoluble. It means the problem is hard in a specific quantifiable way, and that solving it may require either more telescope time than current allocation models support, or new observational strategies that have not yet been fully developed. There is active work on both fronts. One approach involves using the simultaneous observation of TRAPPIST-1b during TRAPPIST-1e transits. Since the 2 planets occasionally transit at nearly the same time, JWST can observe the star during a period when both planets are in transit, and the different chord geometries and spectral signatures can be used to jointly constrain the stellar contamination model. This technique, which the DREAMS team is implementing in ongoing observations, represents a creative use of the TRAPPIST-1 system's unique geometry that no other planetary system currently allows. A second complication involves the planetary interior models that underpin the atmospheric scenarios being tested. When we say that TRAPPIST-1e might have a nitrogen-rich secondary atmosphere, we are making an implicit assumption about the planet's volcanic outgassing history, specifically that the planet has had sufficient internal heat to drive sustained volcanism for long enough to rebuild a meaningful atmosphere after the primordial one was lost. Whether a planet has sufficient internal heat for sustained volcanism depends on whether it has a molten core, which depends on whether it has enough long-lived radiogenic isotopes in its interior and enough tidal heating from its neighbours to prevent the core from freezing. For TRAPPIST-1e, the tidal heating contribution from orbital resonances is estimated at between 0, 5 and 4 times the total tidal dissipation on Earth. a range wide enough to mean the difference between a geologically dead interior and a geologically active one, without a direct constraint on the planet's tidal dissipation factor, a parameter that cannot currently be measured remotely, the volcanic outgassing rate, and hence the secondary atmosphere replenishment rate, cannot be reliably calculated. This is the internal heat degeneracy problem, and it sits at the centre of every habitability assessment we make for the TRAPPIST-1 planets. We know the planets exist. We know their masses and radii to reasonable precision. We know their orbital periods and eccentricities within current measurement uncertainties. But we do not know what is happening inside them, and the interior determines almost everything that matters for long-term habitability. The difference between a planet with a sustained magmatic system producing continuous outgassing and a planet with a geologically frozen interior is the difference between a world that can fight back against atmospheric erosion and a world that cannot. We are trying to read the story from the outside, planet by patient planet, without being able to open the book. A third complication is the question of what kind of atmosphere would be detectable, even in principle, given the stellar contamination environment of TRAPPIST-1, the molecules most commonly discussed as potential biosignatures: oxygen, ozone, methane, CH trait, nitrous oxide, N2O, have absorption features at specific near-infrared wavelengths that JWST's NIRSpec instrument is designed to detect. But the signal strength of these features in a thin, nitrogen-rich Earth-like atmosphere is, for TRAPPIST-1e, of order 10 to 30 parts per million. The current JWST measurement uncertainty on the TRAPPIST-1e transmission spectrum after 4 visits and stellar contamination correction is of order 30 to 50 parts per million per spectral channel. This means that even an exact Earth-clone atmosphere around TRAPPIST-1e, N2-dominated, with Earth-like concentrations of water vapour, CO2, ozone and methane, would be below the current detection threshold. We are not yet sensitive enough to see it. More visits, more integration time, or a larger and more sensitive future telescope are required to reach the detection floor for an Earth-like atmosphere composition. This is not a hopeless situation. It is a situation with a clear path forward. The DREAMS program's 15 additional transit observations are expected to bring the measurement uncertainty down to approximately 15 to 20 parts per million per spectral channel, at which point the presence or absence of a substantial CO2 feature, which is a stronger absorber than most biosignatures, and therefore more easily detected, could be determined with confidence. CO2 is not itself a biosignature, but its presence or absence is a critical discriminator between atmospheric scenarios, because a secondary atmosphere built from volcanic outgassing on a rocky planet almost always contains significant CO2, while an atmosphere stripped down to its lightest remaining components might be predominantly N2 with only trace CO2. If the additional DREAMS observations detect a CO2 feature at the expected wavelength, around 3 micrometers, that would be strong evidence for a secondary volcanic atmosphere. If they detect no CO2 but find a flat spectrum consistent with nitrogen, that would be deeply puzzling and potentially fascinating. A world that has somehow maintained a nitrogen atmosphere while losing most of its carbon. If they find nothing at all, a flat, featureless spectrum across all wavelengths, that would be the most uncomfortable result of all, because a bare, airless planet and a nitrogen-only atmosphere produce very similar transmission spectra, and distinguishing between them at the precision level currently accessible to JWST is, frankly, not certain to be possible even with all 130 hours of program time. This is the knife edge on which TRAPPIST-1e currently balances, and it is genuinely transparently uncertain in a way that I think the public discussion of the JWST results has not fully communicated. The 2025 MIT paper's conclusion that TRAPPIST-1e remains one of the most compelling habitable zone planets, and that its atmosphere is consistent with either a bare surface or a nitrogen-rich secondary atmosphere, is not scientific hedging. It is an accurate description of the current state of knowledge. The telescope is doing its best. The scientists are doing their best. The star is difficult. The physics is challenging. And the answer, when it comes, will have been earned. There is one more thread that deserves careful treatment here, and it concerns the relationship between the inner planet's atmospheric absence and the habitability prospects of the outer worlds. The conventional framing of the TRAPPIST-1 results, planets B and C are bare rocks, but perhaps D, E, F and G are different, rests on an assumption that the same processes that stripped the inner planets operated less aggressively on the outer ones due to their greater distance from the star. This is physically reasonable and probably correct in broad outline. But there is a subtler danger here that some researchers have begun articulating, which is that the inner planets serve as a canary for the whole system in ways that are not solely about their current radiation environment. The pre-main sequence phase of TRAPPIST-1's evolution, that billion-year period of high luminosity during which the star was radiating far more powerfully than it does today, irradiated all 7 planets simultaneously. Every world in the system spent approximately the same amount of time bathing in the pre-main sequence UV flux, with the outermost worlds receiving proportionally less but still enormous doses. The question of whether the outer planets survived this period with enough volatiles to rebuild an atmosphere after the star dimmed depends critically on the initial volatile inventories of those worlds, and those inventories are model dependent in ways that are difficult to constrain from current observations. The density measurements suggest the outer planets have significant water content, but the conversion from density measurement to water content requires assumptions about the iron to silicate ratio of the planet's interior that introduce substantial uncertainty. Some models that fit the density data allow for very large water inventories. Others, equally consistent with the data, allow for much smaller ones. We cannot currently distinguish between these scenarios without either direct spectroscopic evidence of water vapour in an atmosphere or interior seismic measurements that are entirely beyond current technological reach. The pattern of the JWST results, taken collectively, looks like this: a system in which the inner 4 planets almost certainly lack substantial atmospheres, with the case being most definitive for planets B and C and less definitive for D, while the habitable zone planet E sits at the current edge of detectability, with its atmospheric status genuinely unresolved, and the outer 3 planets F, G and H remain less well characterized than the inner planets due to their longer orbital periods and hence slower accumulation of transit data. The overall picture is not an optimistic one compared to the hopes of 2017, but it is not a closed case either. The critical measurement, the definitive atmospheric assessment of TRAPPIST-1e, is still pending, and that pending measurement is arguably the most consequential observational result in the history of the search for habitable worlds. There is something I genuinely believe, and I will say it directly. The scientific community has been unusually candid about the difficulties in this program, more candid than is typical in a field where competition for telescope time and public attention creates strong incentives to overstate certainty in positive results. Gliddon's explicit statement that TRAPPIST-1e is equally likely to have or not have an atmosphere, Espinosa's acknowledgement that even a null result would be scientifically valuable, Gillon's willingness to lead the study that found his system's inner planets to be bare. These are marks of a community that has matured in its relationship with this data. We are not being told the story we want to hear. We are being shown the data as it actually is, including all its uncertainty and incompleteness, and asked to sit with the discomfort of not knowing. That is what real science looks like, and it is something worth appreciating. What comes next is both technically determined: more JWST observations, more transits, more spectral channels, and genuinely unpredictable, because the universe has a way of surprising scientists who think they know what they are going to find, and TRAPPIST-1 has already surprised us more than once. The system that was supposed to be a census of 7 identical Earth-sized worlds has turned out to be a laboratory of diversity, varied densities, varied volatile inventories, varied orbital dynamics, varied tidal heating environments. The inner worlds are bare. The outer worlds may not be. TRAPPIST-1e sits between them, holding the answer to the most important open question in terrestrial exoplanet science. The observations are already collecting photons. The data is already being processed. Somewhere in the pipeline of the DREAMS program, in the reduction codes and stellar contamination models and atmospheric retrieval algorithms of teams at MIT, Cornell, Johns Hopkins, the Space Telescope Science Institute, and the University of Liège, the answer is already there, buried in the noise, waiting to be extracted. The TRAPPIST-1 results, whether they ultimately confirm a surviving atmosphere or a system of bare rocks, will not be the end of the question. They will be the end of the beginning. They will tell us, with more precision than we have ever had before, what happens to rocky habitable zone planets around the nearest, most studied red dwarf star accessible to current technology. What they cannot tell us, what no single system can ever tell us, is whether the TRAPPIST-1 outcome is representative, exceptional, or somewhere in the vast, complicated middle ground between those two descriptions. To answer the representative question requires a sample, not 7 planets around one star, but dozens or hundreds of planets around dozens of different stars, spanning a range of stellar ages, activity levels, spectral types, and orbital configurations. Building that sample is the work of the next 2 to 3 decades of space-based and ground-based astronomy, and the architecture of that program is already being assembled. The Nancy Grace Roman Space Telescope, if it survives its turbulent budgetary history, and as of the most recent available information before mid-2025, it remained on track for a late 2026 launch, will conduct coronagraphic direct imaging of nearby planetary systems, capable in principle of directly imaging giant planets around nearby stars and characterizing their reflected starlight spectra. Roman will not be able to directly image TRAPPIST-1 or any other nearby red dwarf's rocky planets. Those worlds are too small and too close to their stars for current coronagraph technology. But Roman's wide field survey component will detect thousands of new transiting exoplanets, many of which will be rocky worlds around brighter, more spectroscopically amenable stars. Its contribution to the atmospheric characterization problem will be statistical, identifying the best new targets for follow-up with the next generation of ground and space-based instruments. The European Space Agency's Plato mission, currently on track for a 2026 launch following its review timeline, will focus precisely on the kind of Sun-like and K-type stars that are most amenable to the detection of habitable zone Earth-sized planets from the transit method, the same technique pioneered by Kepler but applied with higher photometric precision and covering a wider field. Plato's goal is specifically to find rocky planets in habitable zones around bright, nearby, well-characterized stars, the kind of stars whose planetary atmospheres could then be studied spectroscopically by JWST or its successors during the next decade. If Plato delivers on its specifications, it will provide a catalogue of prime targets whose habitable zone atmospheres can be assessed before the decade is out. More transformative still is the extremely large telescope, the European Southern Observatory's 39, 3-metre ground-based instrument currently under construction on Cerro Armazones in Chile, with first light projected for 2028 and regular science operations expected to begin in 2030. The ELT will be, by a factor of roughly 7 in collecting area, the most powerful optical and near-infrared telescope ever built. Its Andes spectrograph, Armazone's high-dispersion Echelle spectrograph, is specifically designed to conduct high-resolution transmission spectroscopy of exoplanet atmospheres at spectral resolutions capable of resolving individual molecular absorption lines rather than simply detecting broad molecular bandheads. This capability is crucial for biosignature detection because at high spectral resolution, the Doppler shift of the planet's atmospheric lines as it orbits the star allows the planetary signal to be separated from stellar and telluric contamination in ways that are impossible at the lower resolutions currently used by JWST. The ELT will not work on TRAPPIST-1 directly. The star is too dim for high-resolution spectroscopy with even a 39-metre mirror, but on nearby brighter systems it will be, within a decade of first light, the most powerful atmospheric characterization instrument available. For TRAPPIST-1 specifically, the next generation instrument is the LIFE mission, the Large Interferometer for Exoplanets, currently under conceptual study in Europe, which proposes a space-based mid-infrared interferometer consisting of multiple telescope elements flying in formation and combining their light to achieve the angular resolution needed to directly detect and spectrally characterize rocky planets in the habitable zones of nearby stars, including TRAPPIST-1. LIFE would operate in thermal emission rather than transmission spectroscopy, measuring the infrared glow of the planets themselves rather than the filtered starlight during transits. This approach bypasses the stellar contamination problem entirely, because the planet's thermal emission is entirely independent of the star's spectrum. You are detecting the planet directly, not through the star. LIFE remains in the study phase as of the most recent information available before mid-2025, with a potential launch window in the late 2030s to early 2040s if the mission receives scientific community support and institutional funding in Europe and potentially in the United States. It is a long-term aspiration rather than an imminent reality, but it represents the true successor to JWST for the TRAPPIST-1 program, the instrument that would finally answer, not just constrain, the atmospheric and habitability questions the current generation of telescopes can only partially resolve. What makes the next 20 years of this investigation so genuinely gripping is not the technology alone, but the convergence of questions that are now fully articulated and actively being addressed on multiple fronts simultaneously. We know, with the precision that JWST has delivered, what the inner TRAPPIST-1 worlds look like from the outside: hot, bare, tidally divided, stripped. We know with the nuanced ambiguity that the TRAPPIST-1e analysis has exposed that the critical measurement at the heart of the system's habitability is within technological reach but not yet in hand. We know, from the density measurements and orbital dynamics, that the outer planets have characteristics that distinguish them from their inner siblings in ways that make the question of their survival genuinely open. And we know, from the broader theoretical framework of red dwarf habitability, that whatever we learn at TRAPPIST-1 will reshape our estimate of the fraction of the galaxy's habitable zone planets that are actually habitable. There is a specific number I want to leave you with from this chapter, because it captures the stakes with a precision that words cannot quite match. The Milky Way galaxy contains approximately 40 billion rocky planets in the habitable zones of their host stars, according to current estimates based on the Kepler exoplanet census extrapolated across the galactic stellar population. Of those 40 billion planets, approximately 30 billion orbit red dwarf stars. If red dwarf habitable zone planets systematically lack atmospheres, if the TRAPPIST-1 story generalizes, then the effective number of potentially habitable planets in the Milky Way is not 40 billion, it is closer to 10 billion, and those 10 billion are the smaller, harder to detect fraction orbiting the less common, brighter, more solar-like stars. That is still an enormous number. Life could be everywhere in that 10 billion, but the reduction from 40 billion to 10 billion is a fourfold contraction of the cosmic opportunity for biology, driven not by new biology, but by new atmospheric physics. The universe is perhaps a slightly lonelier place than the February 2017 press conference implied. Or perhaps the outer TRAPPIST-1 planets will turn out to have retained their atmospheres. TRAPPIST-1e will return a clear nitrogen-methane spectral signature, and the 40 billion figure will hold. Both futures are currently consistent with the data. Only one of them is true. There is a specific quality to the darkness on the ridge at La Silla that you do not quite expect until you are there. The altitude strips the atmosphere to its thinnest, the dryness of the Atacama eliminates almost every trace of moisture, and what remains overhead is a sky that appears, to the naked eye, almost impossibly deep, a blackness that seems to recede rather than terminate, as though the familiar dome of the night is something only we ever imagined was there, and the universe, which has no ceiling, has always been simply waiting. In the dome of a small robotic telescope on that ridge, something happened a decade ago that was, in its way, as consequential as almost anything that has happened in 20th century astronomy. A sequence of numbers encoded in the dimming and brightening of a red star 40 light years away resolved itself into the outline of 7 worlds. 7 worlds that we have spent the years since learning, one careful measurement at a time, are stranger and more complicated than we hoped. Worlds that are tidally locked and flare-scarred and possibly stripped bare. Worlds whose atmospheres, if they still exist, are so thin and so elusive that the most powerful space telescope ever constructed must stare at them for hundreds of hours to begin to resolve the question of their presence. Worlds that live around a star that will still be burning in its slow red way long after the Sun has exhausted its hydrogen and expanded to swallow the orbit of Earth. TRAPPIST-1 will outlast us. It will outlast the Earth. It will outlast the solar system as we recognise it, still dimly burning, still holding its 7 locked companions in their resonant dance 10 trillion years from now. What we are doing, in pointing our finest instruments at that system, is asking the oldest question in the most precise way our civilization has ever been able to ask it. We are asking whether we are alone, not in the vague, romantic sense in which that question has been asked since the first human looked up and wondered, but precisely, quantitatively, with error bars and stellar contamination models, and 130-hour telescope programs and spectral residuals measured in parts per million. We are asking with everything we have, at the very edge of what we can hear. The answer is not yet in, fully, but the shape of what we have found is already telling us something true and important about the universe. It is telling us that the path from a rocky world in a habitable zone to a world that breathes and drinks and lives is not guaranteed by location. It requires the right star, at the right age, of the right character. It requires an atmosphere to form and survive and persist against the ravages of stellar activity over geological time. It requires, perhaps, the specific combination of size and distance and volcanic vigour and magnetic protection that Earth has. The combination that we spent centuries assuming was common because it was all we had ever known, and that we are now, for the first time, beginning to test against the actual data of the universe. And if TRAPPIST-1e comes back bare, if the 130 hours return a flat spectrum, a bare rock, a 7th world in a sequence of 7 airless stones orbiting a quiet red coal, then what we will have learned is not that life is impossible, or that the universe is empty, or that the search was wasted. What we will have learned is that Earth is more particular than we thought, that the blue, breathing marble we live on is not a default outcome of planetary physics, but a specific, hard-won, statistically improbable achievement of the universe's chemistry and time. That our atmosphere, which we treat as air, invisible, ubiquitous, the background condition of everything we have ever done, is a gift fragile enough to be undone by the simple bad luck of orbiting the wrong kind of star. And if TRAPPIST-1e comes back with nitrogen, with methane, with the ghost of a secondary atmosphere rebuilt from volcanic gases over billions of years of patient planetary defiance, then we will have found something else entirely. We will have found that the universe, given enough time and enough volatiles, and even a hostile star, makes a second attempt. That planets, like scientists, are stubborn enough to try again. There is still more observing to be done. There are still 15 transits, and the analysis of 15 transits, and the debates over stellar contamination models, and the atmospheric retrieval runs on the final stacked spectrum, and the referee reports, and the press releases, and the papers in the astrophysical journal letters. There is still, at the centre of all of it, a planet 40 light-years from this one, orbiting in the pale warmth of a red ember star, holding its answer like a sealed envelope. We sent a telescope to open it. We are still reading the letter.